Good day, everyone. We are Group 1, and today we will be presenting about the fluvial environment, one of the most important depositional settings on Earth. Fluvial systems are shaped by rivers and streams that act as powerful agents of erosion, transport, and deposition. These processes not only create distinctive landforms such as alluvial fans, braided rivers, meandering rivers, and floodplains, but also preserve valuable records of Earth's climate, tectonics, and surface processes. By studying fluvial environments, we can better understand how sediments move across landscapes, how river systems evolve over time, and how these processes influence both natural resources and human activities. In this presentation, we will explore the definition of depositional and fluvial environments, the different zones and types of fluvial systems, the key features of alluvial fans in river systems, and the sedimentary processes and structures they produce. Before we begin, let me first walk you through the outline of our presentation. We'll start with an overview of depositional environments where we'll define what they are and look at the different types. This will give us a foundation for understanding how sediments accumulate and are preserved over time. Next, we'll focus on the fluvial depositional environment. Here, we'll answer the question, what exactly is a fluvial environment? We'll also discuss the different zones within a fluvial system from erosion to transport and deposition. After that, we'll move on to alluvial fans. In this section, we'll define what alluvial fans are, explain their depositional settings, and examine the sedimentary processes that create them. We'll also highlight their main characteristics which make them unique compared to other depositional features. Finally, we'll cover the river system. This part will explore how rivers function as networks of water and sediment transport. We'll look at different channel forms, the causes of river sinuosity and braiding, and the sediment transport process that shape floodplains, levees, and other river-related deposits. So, that's our roadmap for today. Starting broad with depositional environments, then moving step by step into the details of fluvial systems, alluvial fans, and rivers.
Today, we will explore depositional environments. What are they? The major types, and then focus specifically on the fluvial depositional system, with an in-depth look at alluvial fans and river systems. Depositional environments are fundamental to understanding sedimentary rocks and Earth's geological history, because they reveal how sediments are transported and preserved over time. A depositional environment is an area where sediment accumulates through physical, chemical, and biological processes, and later become preserved as sedimentary rocks. The characteristics of these sediments and the rock form depend largely on these processes, such as water flow, chemical reactions, and living organisms active during deposition. Understanding these environments help geologists interpret past climates, tectonic activity, and life on Earth. Depositional environments are broadly categorized into three settings. The first one is the continental or terrestrial setting. These are land-based environments where sediments accumulate. Example includes fluvial systems or river and streams, deserts, lakes or lacustrine, glacial areas, and deltas. And then we have the transitional environment, the marginal marine. This occurs where land meets sea, such as beaches, estuaries, lagoons, tidal flats, and the neritic zone, the shallow part of the ocean over the continental shelf. And lastly, the marine setting. These environments are offshore and in the open ocean, where sedimentation occurs in deeper waters. Each setting has distinct sediment characteristics based on energy level, sediment supply, and biological activity. Focusing on the fluvial system, this includes all processes and deposits related to rivers, streams, and gravity-driven water flow. Fluvial depositional environments can occur in diverse climatic regions, from cold glacial areas to humid forests and arid deserts. Fluvial systems are classified into two main settings: the alluvial fans and rivers. Within this system, we recognize three zones based on energy and sediment movement. The first one is the erosional zone. Here, steep gradients cause rivers and streams to erode and carry sediments from their source rock. It is any area where the flowing water energy is strong enough to detach and transport sediment, soil, or rocks from the riverbed and banks. The second one is the transfer zone. With a gentler gradient, sediments are transported downstream. It is the area where eroded sediments is carried downstream from the source or the sediment production zone to the depositional environment, often occurring in the midstream of or river valley sections with a lower relief. The last one is the depositional zone, where water velocity decreases, leading to sediment deposition. It is the area where river water slows down, loses its energy, and drops the sediments it has been carrying. Understanding these three zones is the key to interpreting sediments distribution in the river system. What are alluvial fans? Alluvial fans are cone or fan-shaped sediment deposits that typically form at the base of mountain fronts, where steep slopes meet a flat valley floor. They are composed primarily of poorly sorted sediments, often dominated by gravel-sized clasts. These fans form as water flows rapidly down steep slopes, carrying sediments that spread out and deposit as the gradient decreases sharply. In geological and geomorphological literature, alluvial fans usually describe unchannelized or poorly channelized sediments accumulations on steep slopes. Alluvial fans commonly form in arid or semi-arid regions after intense rainfall events, when large volumes of water rapidly descend from high relief areas. Sediments are transported downslope and deposited as fans. In deserts, these fans often form on internal drainage basins, where water does not reach the oceans. In humid climates, alluvial fans can merge downslope into other environments like alluvial plains, deltaic areas, beaches, and tidal flats. This merging reflects a continuum from steep mountainous terrain to coastal or lake environment. Alluvial fans develop through two primary sedimentary processes. The first one is the debris flow dominated fans. Debris flows are rapid, viscous mixture of water and sediments, carrying a wide range of particle sizes from clay to boulders. They typically deposit poorly sorted, matrix-supported sediments that are often impermeable and non-porous. Debris flow tends to stop after short distances and occurs where slopes are steep and vegetation sparse. Mud flows are a similar process but contains more sand-sized and finer sediments. The second one is the stream flow dominated fans. These develop from fluid flow mechanism and include sheet floods and incised channel flows. Sheet floods are unconfined water flow spreading sediments over a broad area, usually following intense, short-duration rainfall. Incised channel flows, this flow commonly include flow confined within channels that 1 to 4 meters deep. Sediment concentrations in stream flows are typically about 20%. Higher concentrations between 20 to 40% are called hyperconcentrated flows and exhibit mixed debris flow and stream flow characteristics. Alluvial fans are typically cone-shaped with a network of branching distributary channels visible in plan view. Fanhead, the upper part near the mountain front, where sediment tend to be coarser and poorly sorted, while the fan toe, the distal edge of the fan, where sediment gradually become finer and better sorted. Debris flow deposits tend to be poorly sorted, coarse, and muddy. In contrast, stream flow deposits are more layered, with features like cross-bedding, lamination, and better sorting of gravel, sand, and silt. One distinctive feature of the alluvial fan is the sieve deposit, coarse materials that settles quickly as water percolates through previously deposited permeable sediments, causing immediate sedimentation. Sediment grain size generally shows no consistent vertical trend, but some fans display upward coarsening due to ongoing deposition, while others show finding upward pattern indicating periods of inactivity or retrogression. Alluvial fans plays an important role in shaping landscapes and preserving geological records. Their deposit tells us about past climatic events, sediment supply, and tectonic activity.
A river system is a network of streams and rivers that transports water and sediment across the landscape, such as a lake, sea, or ocean. However, not all rivers behave the same way. The shape and structure of a river's channel or channel form can vary greatly depending on its energy, sediment load, slope, and the materials comprising its banks. Channel form refers to the physical layout or pattern that a river channel takes as it moves across the landscape. The two main types of channel forms we'll focus on are braided and meandering channels. Each has distinctive characteristics and forms under different environmental conditions. Let's start by looking at the first channel form. The braided rivers often contain mid-channel bars, which are sediment deposits usually made of sand and gravel formed within the middle of the river channel. These bars are not permanent landforms as they can become submerged during bankful flow and reappear as water levels drop, dividing the river into several smaller channels. The channels in a braided river may also be sinuous, meaning they may curve gently rather than flow in straight lines. Additionally, braided or bedload rivers are typically found where there is a high volume of coarse sediment, such as gravel and sand, that moves along the riverbed by rolling or bouncing, a process known as saltation. In a braided river, the presence of multiple bars causes the river to split into several channels, creating a braided pattern. These bars contain different shapes that form within the channel, and each bar type forms under different flow conditions. Longitudinal bars are relatively flat, and as they slowly migrate downstream, they create sediment layers that are gently inclined and not very distinct, a phenomenon known as low-angle cross-stratification. In contrast, transverse and lingoid bars are taller, and as they form and move, they produce more prominent and easily recognizable layers of sediment that slope downward in the direction of river flow, known as well-defined cross-stratification. Water moving between these bars carries and deposits the coarsest material shaping the riverbed, and gravelly bars may become conglomerates while sandy bars often exhibit underwater dunes. When the braided river frequently shifts position across the alluvial plain, braid plains are formed. It is described as the wide sediment-covered surfaces which are characterized by their multiple, shifting channels separated by bars of gravel and sand. Over time, as these rivers migrate laterally, constantly eroding and depositing material, the entire surface of the alluvial plain becomes covered by a complex pattern of channel deposits and bar forms. They are also typical in areas with high rainfall or low vegetation such as glacial outwash plains because these areas deliver a high supply of loose sediment and are subject to fluctuating water discharge. When a river flows through loose material from glaciers or heavy rain, and there are few plants to hold the banks together, the river breaks into many shallow channels that keep changing their paths. The last channel form we're going to focus on is the meandering river. A meandering river follows a single winding path called the talweg that curves back and forth across the landscape. This form is more common further downstream where the river has a lower slope and carries finer sediments. Meanders develop as fast-flowing water erodes the outer bank and slower flow on the inner bank leads to sediment deposition. Lateral migration of the channel and the formation of point bars. Lateral migration refers to the sideways movement of a river channel as it erodes its outer bank and deposits sediment along its inner bank. This process creates point bars, crescent-shaped deposits that form on the inside of riverbeds. Point bars display a characteristic spining upward sequence, meaning the sediment becomes spiner from the bottom to the top as the river's energy decreases toward the inner bend. These deposits often show cross-bedding and cross-lamination, which are inclined layers formed by the movement of sediment in flowing water. Within point bars, lateral accretion surfaces, also known as epsilon cross-stratification, are formed as the channel migrates. These surfaces are typically low angle, less than 15 degrees, and record the gradual sideways build-out of the point bar, providing evidence of the direction and extent of channel migration over time. As lateral migration continues, the bends in a meandering river can become so pronounced that during a flood, the river may cut across the narrow neck between two loops, creating a shortcut. When this happens, the old meander loop is abandoned and becomes an isolated oxbow lake, which gradually fills with fine-grained and sometimes organic-rich sediment. During such flood events, new shoot channels may also form as water shortcuts over point bars, leaving behind distinctive scour marks and sometimes containing mudclasts eroded from the river's cohesive banks. Why do some rivers meander while others spray? River sinuosity or meandering typically develops where channels have gentle slopes, cohesive fine-grained banks that resist erosion, and a predominance of suspended sediment encouraging lateral migration and the formation of meanders. In contrast, river braiding occurs where channels have stiffer slopes, banks made of easily eroded coarse material, and a high bed load of gravel and sand, resulting in unstable channels that split and shift frequently, forming multiple intertwined channels separated by bars. Rivers move and deposit sediment in several ways, but before delving into this topic, let's first know the importance of sediment transport. Sediment transport is fundamental to the formation, evolution, and maintenance of sedimentary environments and landforms. It connects the processes of erosion, transportation, and deposition, which together create and modify the Earth's surface features. And now, let's take a closer look at the first way to transport sediment, which is the channel transport. It is the movement of water and sediments through a river or stream channel. And as water flows within the confines of the channels, it carries sediment that moves through river channels as bed load, the rolling or bouncing along the bottom, suspended load which is carried within the water, and dissolved load, the material in solution. The type and amount of sediment transported depend on water flow, slope, and sediment characteristics. According to Nichols, most coarse materials remains within the channel during normal flow, while finer sediments can be carried further downstream. The next one is the floodplain or overbank deposit. When the river discharge exceeds channel capacity, water flows onto the floodplain, also known as overbank flow, depositing suspended materials like silt and clay. Coarser materials settle first, forming thin layers that may display current riffles or horizontal lamination, while finer clay remains suspended and will be deposited as floodwaters recede. The third one is the natural levee deposits. It is a bank of sediment that forms along the edge of the river channel and develops as repeated floods deposit sand and silt near the channel bank. And through time, ridges of sand and silt along channel banks that can eventually raise the channel above the floodplain. Lastly is the crevasse play. It forms when a natural levee is breached. Sediment-laden water forms a crevasse play, a cone-shaped deposit that coarsens upward as more sediment flows through the opening. Nichols notes in his book that such depositional processes are central to the development of alluvial architecture, with crevasse plays and natural levees playing key roles in floodplain evolution and at times leading to channel avulsion, which means the river adopting a new course.
And that concludes our presentation on the fluvial environment. We have seen how depositional environments shape the Earth's surface with a special focus on fluvial systems, covering their zones, processes, and landforms such as alluvial fans and river systems. By understanding how rivers erode, transport, and deposit sediments, we gain valuable insight into Earth's history, landscape development, and even natural resources. On behalf of Group 1, thank you for listening.